In this segment, I want to introduce you to some very scary things about regression analysis. And hopefully comfort you so that you're not so scared of them. And so I call these Grimm's fairy tales for epidemiologists. Now why? Well, Grimm's fairy tales serve a very useful function. You know, we take care of our kids, we comfort them when they're hurt, we tell them that everything's okay. But in reality, it's a scary world out there. And so Grimm's fairy tales are a way of talking about other children, not you, but Hansel and Gretel, and scary things happen to them. And that's to prepare children for the fact that things really are a little scary out there, you know. And when you graduate, you're going to have to look for a job. That's scary, right? You know, and we need to get people prepared for that. So similarly, let's get prepared for some of the scary things about regression. There is scary data out there, data that doesn't behave well. What are we going to do about that? Well, here are the typical big bad wolves for linear regression, right? And people have probably told you that linear regression assumes that the data is normally distributed, right? Well, first of all, they lied. That's not what linear regression assumes. Linear regression assumes that the errors are normally distributed, that the difference between what your model predicted and what the actual observations were is normally distributed, okay? And that's a big difference because suppose your data is skewed. I have blood lead levels, right? For example, something I've studied a lot. Well, there's actually a lower limit for blood lead levels, right? It can't go below 0, right? Because we don't want antimatter in your blood. Okay? So, whereas it can get very, very high if you're in a very exposed environment. So it tends to be skewed. But if I have the variables that predict your blood lead level well, including, for example, are you living in a very exposed environment, then I might very well, and indeed hopefully, explain why the distribution of blood lead levels is skewed and my errors could still be normally distributed. So there's a big difference between the data being normal and the errors being normal. And that is that hopefully if you have the right predictors, the right exposure variables, you can explain the non-normality in whatever outcome you're looking at, and your errors will still be normal. So never look at the data to decide whether this assumption is violated. The second thing that we assume is that the errors are independent. And again, this is an assumption about the error, not the data. So for example, if I recruit people at 5 hospital centers to take part in a study, and I recruit some cancer cases and some control, stuff like that, hospitals draw on different populations, and so there's going to be some correlation between people who go to the same hospital because they're more alike than average. But if I control for hospital in my analysis, then the errors are going to be independent. Constant variance. Now what that means is the following. this is not constant variance, right? This is some outcome. This is some predictor. Here's a line through the data, and the variation around the line, the variation of the error, not the data, keeps getting bigger and bigger, right? So that's not constant variance, and from this I hope you can figure out what constant variance is. That's another assumption, okay? There's also outliers. That's pretty scary stuff too. Again, if someone has a very high value and you have a predictor that explains that, you don't have an outlier. Outliers are also something about the errors, not the original data, okay? So that's about the errors. And then we have one assumption about the expected value of the data, which is this linearity. But we already talked about that, and we know how to relax that. You put in another term that's either also linear but in a different range of exposure, or it's quadratic, right? We just add some additional variables. So we know how to deal with that. So let's talk a little bit about the rest of these big bad wolves and see what the story is. Here's my basic message. It's not so bad. Really, the fact that the data doesn't meet your high expectations, son, I'm disappointed in you, right? You know, the kid's gonna be all right. And the reason is that least squares regression is robust. If some of the assumptions aren't met, in general, you will get unbiased estimates of your slopes, of your betas. It's pretty good at that. Data not normal? It's not so bad. In fact, the data doesn't have to be normal. The least squares regression, it not only gives you an unbiased estimate of beta, it gives you the unbiased estimate. There's more than one way to get an unbiased estimate, by the way. It gives you the one that has the smallest confidence interval under more relaxed assumptions than the data being normal. Now, normality is good, but the data doesn't have to really be normal. If it's really non-normal, the errors, then you start getting into trouble. But we have ways of fixing that. And so we'll talk a little bit about that in this course, okay? Now, what about the data not being independent? Again, that doesn't bias your estimated slope, but it does bias the confidence interval. Usually you get ones that are too small. A, we're going to learn how to fix that. B, you know, if you can't fix it, you can always say, well, you know, I'm going to make sure that the p-value is less than 0.02 instead of 0.05 and forget about it, right? You know, because it's an unbiased estimate, right? So for least squares, linear regression is robust. And if your variance varies, as I showed you, well, again, there's no bias in the coefficients, but the confidence intervals are wrong. And again, in this class, we're going to learn how you fix that. So let me talk briefly about the issue of the data not being normal with a little bit of a warning. So let me come back to the example I mentioned to you about blood lead. Okay? Imagine this is the distribution of blood lead. I have blood lead levels going higher, and here I have, let's say, the number of children. And I get some distribution that looks like that. Now, many of you can probably look at that and say, you know, that looks like a log normal distribution. No problem. I take the log transform, and transformations are useful things. And so instead of regressing blood, lead against age and various other predictors, why don't I regress the log of blood, lead against age and various other predictors? Well, you can do that, but what you need to remember is transformations are a way of fitting a dose response curve. They're an alternative to putting in quadratic terms to fit a nonlinear relationship. And so when you go from here to here, you're specifying a nonlinear dose-response relationship. Why? Because if I say the log of blood lead is equal to that, then if I exponentiate both sides, this model says that blood lead is e to the b0 plus b1 age, plus, let's say it's e to the b2 times sex times etc., right? And here I separated age and sex because when you exponentiate a sum, that's like the product of the exponentials. So this is fitting a pretty nonlinear relationship with age. And in fact, right, if I look at, let's say, blood lead versus age, right, I think that it's going up pretty fast. So maybe that's true, but maybe it's not true. And the point is, when you're doing this, you're changing the dose response curve. You may not want to do that. And fortunately, there are other ways to deal with the data not being normal that don't require you to do that. So this is not a bad thing to do if you think it really does look like this. But that should be the criteria for making the choice, not what does the distribution of the data look like. And again, of course, if you've got the right exposure variables in here, they're going to explain this distribution, right? Why are there people out here? Because there's this thing called paint lead that some people have exposure to and some people don't, and it's a big source of lead, and so that pushes that curve out. If you know their paint lead exposure, the residuals may well be normal. And if not, we're going to learn later in the course another alternative for dealing with the situation where no matter what you can do, the residuals still don't look normal. Okay? So those are the big bad wolves, and this is how we're going to deal with them in the course so that you cannot worry and be